Hey folks, Kyle Pearson here. Today I'm going to show you how to use my automated data reduction pipeline to reduce your images that you obtain from some telescope. The intent of this program is that it will create a series of IRAF scripts that will perform all of the necessary data reduction steps that you'll need, that will leave you with calibrated images that you can then use to model and use for your research. The script will do everything from biasing and flat fielding and then picking out the best reference stars that will reduce the atmospheric variations in your images the best. If you guys have any questions about how the program works, feel free to open up the source code and try and read it. It's written in C. I tried to document it as best I could, and some of the IRAF scripts that it creates are documented as well. If you still can't figure something out, feel free to email me. Alright, before we begin, there are a couple requirements that you'll need before you can use this program. So to download the program, you'll have to go to uaastroclub.org /Kyle-Pearson/ExoDRPL Exoplanet Data Reduction Pipeline. So you can download it onto your computer if that's where your images are, or you can download it through the terminal if your images are on a server. There are a couple requirements. You'll need a GCC or G++ compiler, an XGterm, DS9, and IRAF. Most universities will supply you with this software, although it is available on the web. Another requirement is that you'll have to have images, flats, and biases. I'll show you guys the proper format of those in a bit. Also, you should be familiar with the basic photometric reduction process, so you know why the script does the things that it does. Alright, so I'll run you guys through this from start to finish. I'll have to connect to my server where all of the So first thing we'll have to do is start an IRAF window. Log into IRAF. And then you'll have to go to where your data is. I'll be reducing images on hat P16B. Alright, so the basic format for this, you'll have to have images of the FITS format. You'll need to also have biases and flats of a format similar to this. The README file for when you download this program will tell you more in-depthly about the type of format these things should be in. So let's go ahead and download it. We'll have to copy this right here. Go back to our IRAF window. Remember to add the exclamation mark in front of something if you're doing it within IRAF. And now we'll have to untar this. You notice that a couple files come with this. Alloc array. It's just an efficient way to allocate memory for multidimensional arrays. Compile and run is the quick and easy way to compile and run this program. The source file for this, a README, goes through basic instructions on how to use it, and then a source information file that's a little bit more in depth than the README and tells you about what the source code actually does. And then another script down here, stcoox, that attaches the RA and DEC to the header of each image. And this setup task parameters that just gets your IRAF tasks ready so that the program can run smoothly. So the first thing we'll have to do is let's remove one of these XY files from here. That was from last time. Now we will do the compile and run. So you'll want to enter the name exactly as it appears on your images right here, hat P16B. It is case sensitive, so be careful of that. You'll have to find the RA and deck of your planet as well, so just go to your favorite exoplanet website to find that information. Formatting isn't crucial, although it's probably best that you use the standard format. It's easy to read. It should be able to read in fancy characters and stuff like that if you have a preference to using those. Alright, so you'll notice that a couple files were created. The first one is the main script file that will do all the flat fielding, biasing, and get your images ready for the second part of the photometry reduction process. Then we have a README file, a make RHJD, a cleanup file that will remove all of the images that the program has created, and it will leave your original images. It will not delete those. And so first thing we'll have to do is execute this first script. So you'll notice that it loads a couple programs at first and then goes on to create your super bias by combining all of your bias images. You should have all of your bias images and flat images in the same folder as your normal reduction images, and if you have a folder by any chance named bias or flat, you may get a small error when the program goes to run because it does not like to overwrite previous files in your directory. So let's scroll up here. Notice that the standard deviation goes down after biasing, which is good. That's normal. The mean of the super flat is 1. That is also good. Something that you should check. So now it goes on to flat field all your images. So this part will attach that RA and deck information to the header of each image. Just hit enter for these expressions. Okay, now we are on the first part of the photometry process. The program, as you noticed, will open up DS9 automatically. So what we'll have to do here is create an XY file which contains the coordinates of your host star and your reference stars. So we go to scale, z-scale, zoom to fit to get a better look at our image. Alright, looks pretty good. But now we have all these stars. How do we know which one is the right one? So once again, we're going to have to go to, I prefer the Check Exoplanet website because it is easy to navigate and it contains an image of your star. So you go over to your planet right here, show transit predictions, and a nice little image pops up pointing straight to your star. So it looks like it's this bright star right here in the middle with this. Okay, so let's look at our image. That looks to be about our star, and there's this little tail of stars right here that matches up right there. Alright, that's good. So now the first thing that we'll have to do is create the XY file. So I print out instructions on how to do that. In IRAF you'll have to type imexam with a little greater than sign to XY file. I'm going to name it XY file 2 because I already have an XY file 1. So it'll say the display frame, which is the DS9 image. So we come to our DS9 image here, and now in order to choose this star we have to scroll over it and we press comma, and you'll see a little blink or something, and now that information on that star has been written out to XY file too, which we'll open up here in just a second. So now what we'll want to do is choose a couple different reference stars that are around our image. The program will then analyze these stars later to pick out the best combination of them. So you'll want to try and pick out some stars that aren't too faint and aren't too bright as well. And you kind of want to get them evenly spaced around your star as well. You'll want to pick stars that aren't clumped up close together like these two. This may give you a bad reading. Also, the program should decipher which stars are variable and which stars are not, although sometimes it doesn't, so in the end I'll show you how to check for that. So now once we picked out our reference stars, we'll need to find a section of space, about 100 by 100 region, that has no stars in it, so we can obtain the standard deviation of just the sky. So let's come over here, and to do that you come to some region. You can see up in this little window here, and you press M to get the information of it. So we'll want to do that for a couple different regions because we don't know which one's the best. Okay, now once that's done, we press Q to exit out of ImExam. And we can exit out of DS9 for now as well. And we will want to gedit our XY file. Okay, so you'll notice that we have a bunch of information here. We have the information on all of the stars that we picked out and the section information that we picked out earlier. So now what we'll want to do is we have to prep this XY file for the program. We'll have to delete all of the headers, delete all this excess information, and we will want to only keep the X and Y coordinates of each star. Now, what you'll want to do is when you make your XY file, make sure that you name it exactly the same as this up here, XY file. So here, you guys didn't even see what I was doing. So we have all this information. We want to delete it all so that we only have the X and Y positions of our stars. And now with underneath this we have the section information. What we'll have to do with that is we'll need to remember one of these values for the standard deviation. Probably the lowest one is good. So 9.101. Alright, so now that our XY file is prepped and ready, we'll come back here and we'll have to type in 9.101. This will set a certain parameter for a task that will be used later in the program. Now another thing that you'll have, so first off, if you forget any of these steps, you can also open up this text file right here. It contains all of this information. So after we're done with this, we'll need to obtain some information on the number of ingress and egress data points. So to do that, the program creates a file called ut.txt. What that does, or what that is, it has all of your images with the UT time that the image was taken at. And so what you want to do is you want to go back to that Check Exoplanet website or another transit website of your choice, and you'll have to cross-reference the beginning of the transit times with these times and the out-of-transit times with the later ones, and determine approximately how many data points you have. But since I've already modeled this before, I know I've got about 50 data points on the ingress and 50 data points for the egress. So I will not go in depth on how to do that. So now we carry on to make RHJD, and this will create, so we'll want to type in the name exactly as it was before, and this will create all of the info files that will be used to that the program will then analyze afterwards, and it'll determine which reference stars are the best and which aperture is the best. So you have a D-annulus. Before, when you're looking at your DS9 view of your first image, you want to make sure that you picked out some stars that aren't too close together, or they're not close to some sort of line on the CCD like you saw earlier. So my D-annulus I'll set to be about 20, that corresponds to 20 pixels. The annulus I'm going to set to 16. The highest aperture that this program goes up to is 15.9. There is a way to change that in the source file, which I'll show you guys in just a second. It's pretty easy to change. If you have an autoplot.log file, it can read it in. The autoplot.log file contains information like the full width half max of each image, the amount of pixel drift from the auto guider, information like that. I ran some tests, and you can just say no and set the average full width half max to be about 4.5 or 5. It will not mess up your data too much. There's no significant variations in it in the end. So now that it created all this info files, it needs to know how many ingress and egress data points you have. So I'll say about 50 for each. And so now you have to make an RHJD that will later be used for the modeling package. The modeling package is found back here on Exoplanet, on the Astro Club website, ExoMop right here. I'll tell you guys about that in the end. So we just type in what we have here, %1 minus, so this number is this number right here. We want to check to make sure that they don't vary too much, so 245 6290. You want to type this in exactly as it appears, otherwise sometimes it can give you an error. If you get no errors, then you're good. So before we go into the part where it actually runs through all the different apertures, I'll show you guys first about how to change the minimum and maximum apertures that the program runs through. So we open up the source file. It's documented. You guys can read it. So we scroll down here, and then there's some global variables that are used right here. Max aperture 16, minimum aperture 5, and then the precision that it goes by right there. So you guys can change that up accordingly. Sometimes it's best to run through at about 0.5 or even 1. It'll make the program run a little bit quicker, and then once you sort of get a range of where you think the best aperture is, you can go and fine-tune it so that it can run between those apertures and it doesn't run through all of these, because sometimes it can take a little while. So let's go and now create this, or run through the reduction process. So now it will create your mag files, and it'll run through each aperture up until it hits the end. This part can take a little while depending on how many images you have. Let's see, what else can I tell you guys? We'll come back to this when it's done. Alright, just checking in again. So the program is still running. This is what it should look like. This is what you get when you guys run it. That is good. Alrighty, so it's been, I don't know, maybe 20 or so minutes, and it's about to finish up here. And so I'll show you guys what to do after it finishes all the aperture files. So it creates all of the aperture files, creates an all-flux. The all-flux contains the information on all the flux information of each of your stars that you picked out in your XY file. It'll then go through and analyze each of the all-flux files, and it'll pick out which one has the lowest. Yes, already, here we go. So it goes through each of the all-flux files, and it calculates the standard deviation of the ingress and egress baseline. It goes through and does this for each of your, it uses a combination of your reference stars, and it finds the minimum standard deviation. So it can work for anywhere from 1 to, I believe, 10 reference stars. So it looks like a pretty standard reference star is the second one. So these are just the pre-results, and then once the pre-results are analyzed, to avoid having you sit through and try and figure out which one's the best, the program go ahead, analyzes the results. All-flux 6.8 is the best, and your best reference star is number 2. And so now what you have to do is, let's open up an Excel file here. So we go, gedit all-flux 6.8. This is what it looks like. We're going to have to copy all of this information. That's what it looks like. We're going to have to copy all of this information into our thing, and we now do our main star, which is the first one. Hopefully, it will give you the wrong results if your host star is not the first one. And now it goes to the second reference star, so this is 1, 2. And now we can do a quick little plot here. Insert chart, and we have our first light curve. Well, so now what we're going to have to do, so that looks pretty good. Let's check out our error bars. So after our program analyzes the best all-flux, it'll go back and it'll read in the all-flux, and then it'll go ahead and calculate your error bars for you with this reference star and do error propagations with it so that it does everything that's necessary. So pretty small errors, looks pretty good. So let me come back down here. We have to do insert Y error bars, cell range, same for both. Do L1 to L315, I believe it is. Whoa. Does not look right, so let's undo it. Insert error bars again. Oh, here we go. Okay, those look more reasonable now. Alright, so we now have the error bars and everything on our, let's scooch this up, on our transits. And so now the last thing that we'll have, well, there's a couple more steps. So we first have to normalize this light curve by the out of transit baseline, and what we do for that. So we said before that we had about 50 data points for the out of transit, so we come up here from 315, let's come up to about 265 there. We get an average. We're going to insert a column, not where I wanted it. Insert a column. Divided by our average, which is 4.990431864. Alright, let's insert another column. Now what we're going to do is extract that information from the RHJD file. So we go back to our XG term. The RHJD is just a reduced version of the HJD time. The reason that we subtracted off that really large number from the HJD is that when we put it into our modeling program, the sensitivity of the program doesn't really like those large numbers with the small decimal points. And since it needs to be able to figure out where the mid-transit time is, it's best to just take off that big number and add it back on later. Okay, so now that we have these 3 rows here, let's graph it and see what it looks like. Delete that old one. Insert chart. XY sketcher. Finish that. Delete that. Oh, one thing that I forgot to do. Be sure that, let's insert another column here, that you normalize the error bars by the average of your out of transit baseline as well. Otherwise, you will obtain error bars that are extremely large. And then, so once we do this, we can get pretty much a standard image of what our light curve will look like in the end. Alright, let's see. Alright, not a bad light curve. There's a little bit of a scatter towards the end. It was probably due to clouds or something. Now the next step is we will have to copy those 3 columns of your gedit, and let's just say we have the date, December 29th, hat p16b.dat. And now we paste all that information in there. I don't think the formatting is really too important. The modeling package should be able to read it in. But you just want to make sure that you have the contents of your RHJD. Okay, so here we go. We pasted it in. You want to make sure that you have the contents of your RHJD, your normalized light curve, and then your normalized error bars. We will need this file for the modeling package. You can run it through the package tap, or we made up our the University of Arizona now hosts its own modeling package that I will show you guys right now. So you can come to this website. Once again, you can download it through your terminal, and then you just input some basic information about, you just get some values from the discovery paper, plug it into the modeling package, and it'll model your light curve and derive your parameters for you. And then once you figure out the best model, you're ready to write your paper. And that's pretty much the whole program. If you guys have any questions, comments, or concerns, feel free to email me once again. I can be reached on the University of Arizona Astronomy Club website, www.uaastroclub.org. Thanks. Hope you guys enjoy.